Okay, so this lesson's known as curve sketching. It's basically going to be looking at all the different parts to draw a curve. 99% of this you never actually do today because we have a calculator that can graph it for us. You have to remember that most of math was invented pre-calculators and computers. However, that does not mean that the concepts we're learning actually isn't useful. So we're still looking for mins and maxes. Those are important for optimization problems. We're still looking for what we're going to talk about, concavity and curves and how fast things are changing. So those things that we're using to do curve sketching is still very useful. The nice thing is that the ALEKS program, where you're going through and doing the topics for this one, does not require you to sketch a curve. It's actually having you use the pieces to understand what's going on with it. So that's good. We're not actually going to be drawing an actual equation or a function. So the first thing, this one should be pretty obvious based on what we've talked about quite a bit about the first derivative. The first derivative will tell us where the function is increasing and where the function is decreasing. So if the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. So based on that, if we find those zeros, we can determine where, and then look at either side to figure out where the functions are increasing or decreasing based on that. This goes back to what we talked about last class with finding critical numbers. So let's look at a problem. So step one, find me the derivative. Huh? And remember, when you're doing these, like last time, simplifying them is going to help you find the answer easier. All right, so we've got the first derivative. What's the next step we have to do? What do we look for last class? Zeros and what? Where it doesn't exist. So in essence, when we're looking at a rational function like this, we're looking at the top and the bottom. When does top equal 0? When does the bottom equal 0? So 0 equals negative 6x squared plus 54. So x squared can never equal negative 9, so I don't have to worry about, there is no values that the problem doesn't exist on. Remember, when you do the square root of something, if the square root is not there, it is the plus or minus of that number. So we have a +3 and a -3. So those are my critical numbers is ±3. Now, when we're trying to determine where it increases and where it decreases, the easiest way to do this is kind of like you used to do when you did inequalities. Draw a number line, plug some values into the problem. But when you're plugging them in, you're plugging them into the actual derivative in this case, because that's what we're looking at as a greater than or less than 0. So if I have a number line, I got -3 and 3. So I know those 2 points there. So pick a number in each spot, plug it in and test it. So let's do -5, 0, and 5. All I'm trying to figure out is if f(x) prime of x is greater than 0 or f prime of x is less than 0. So all I need to know is it positive or is it negative? I actually don't care what the number is when we're doing this. We just care if it's positive or negative. So the bottom, can the bottom ever be negative in this fraction? No. So I don't care about the bottom. All I care about is the top. Because if the bottom's always going to be positive, we can ignore it. That saves you time, that saves you work. Okay? So I know my bottoms are always going to be positive. So now we're going to look at the top. So if I plug in -5, so 25 times -6 is -150 plus 54. That's going to be negative. So that's positive. And that's negative. Okay. So it is increasing from -3 to 3. It is decreasing from -infinity to -3. Union 3 to infinity. That's how you'd write it. You can never increase or decrease at a point, so they're always parentheses. They're not the brackets for where it equals. Does that part make sense? It's just a natural progression from what we were doing on Tuesday and from the whole concept of what derivatives are. The next piece we can look at is what's known as the first derivative test. Because remember, the goal is to figure out if it's a minimum or maximum. So those are really the ones we're trying to figure out when we're looking at the critical numbers. So if the derivative changes from positive to negative, then it's a local maximum, because that means it's increasing into it and decreasing out of it. If it's changing from negative to positive, then it is a local minimum, as it would be decreasing in and increasing out. If there is no change, then there is no local min or max. Okay. So that last one is a very important rule, because what a lot of people will do is they'll find the first one and then they'll make the assumption that it just switches every time you have a critical number. But remember, we looked at that on Tuesday. We had that problem where we found a critical number and it didn't change. It was still increasing. So that does not mean every time you find a critical number that they are going to switch direction. You have to do them all out to find that out. Sometimes it will, but not always. All right, so we've got these. The next thing that you can be asked for this is, where are, where'd my problem go? So where are the local min and max? Now this is where we go back to our original problem. So in this case, let's go back to the original problem. So if we're looking for the actual original minimum and maximum, or the local min and local max, we're going to take those critical numbers where it's actually changing direction. So this one right here is it's decreasing in, increasing out. So that's a min, and that's a max. We take the critical number and we plug it back into the original problem to find the y value, and then we can have those points. So -1. And then f of 3. So I have a min at -3, -1, and a max at 3, 1. Now, are you going to have to find this for every single problem you ever do? No. But you could be asked a variety of those types of things for different situations you're going to be doing. Any questions with those? All right. Find me the derivative of this. Yeah, right in the box. You're welcome. How many people did the quotient rule? This is where practice comes into play, figuring out the easier ways to do problems. There was only a 1 on the top. If there was a variable on the top, like the last problem, you have to do quotient. No real easy way around it. Technically, I guess you could do the product rule if you move it up top. But if there's a number, just a single number up there or a constant, even if it wasn't a 1, if it was a 5 or anything, it's actually easier to move it up and just do the chain rule. So you don't have to worry about doing all the breakdown of that piece. Plus, with the plus 4x afterwards, you can't do the quotient rule for the whole problem. You'd have had to actually either you'd have done the product rule or quotient rule for 1/2 and then have to do the other piece anyway. So it actually works out better this way. It should have come out to be the same answer. It's taking you a little longer to get there. All right. So we found our derivative. What's the next thing we got to do? Yep, find my critical numbers. So unfortunately, this one I don't have a top and a bottom. So I kind of have to do the whole problem. And this is where remembering your algebra skills comes into play. All right. Any questions on the steps I used to get there? Do I have any other? So that's the zeros. The other thing I have to look for is where the problem doesn't exist, right? Do I have a situation where the problem doesn't exist here? Yeah. When x is -2, it's going to make that bottom 0. So I also have to add in it isn't in the domain of the original. You're absolutely right. No, it is not in the domain of the original. You're absolutely right. So correct. But I always want you to look for them. Never make that assumption until you actually look at it. But you're absolutely correct. In this case, we're not going to need to lose that critical number because that critical number doesn't exist in the original problem. So That would have been the next question I would have
Sorry.
had. You're fine. You're good. You had exactly what I was going to say. So yes, that one doesn't exist because it'll make the original problem 0. So the critical numbers have to exist in the original domain. This one does not. So I do not need that one. However, the one thing I don't want people to do, and this is always that fear. It's like, oh, well, it's always going to end up being there, so I don't have to worry about it. Don't do that. Because it might work for majority of the problems, but it's those problems where it doesn't work and you completely forgot about doing that you're going to go, why am I getting this wrong? So those type of things. All right. So we got our two numbers. Now what do we have to do? Yeah, and now I have to figure out where it's increasing, where it's decreasing. Okay. Pick me a number before -5/2. Actually, you got to go further. Yeah, so -3. And what number do you want to pick between them? Can you? Great. What's -2 do? Didn't we already figure out that doesn't work? That runs into the problem, right? So I was waiting for somebody to say it. I was waiting for that number. Can't pick negative. We can pick any other number. We just can't pick -2. Yeah, this one actually, this part right here becomes a little more complicated. Let's pick 2 1/3. So -7/3. And 0. All right, plug those numbers in, find out if it's positive or negative. you should get a positive on the -3, a negative on the -7/3, and or whatever number you chose in there, and a positive on the 0. So we have it's increasing from -infinity to -5/2 and -3/2 to infinity. It's decreasing from -5/2 to -3/2. So -5/2 and -3/2. What is -5/2? What is that? A minimum or a maximum? It's a max. -3/2. That is a minimum. Okay, find me the values of each of those. When you're finding the min and max, you're plugging it back into the original problem. If you plug it in F prime, you should get 0. That's why it's a critical number. No, you're plugging the -5/2 and the -3/2. So when you're looking for the increasing and decreasing, you're plugging those three numbers into the F prime of X. When you're looking for the minimum and maximum values for the Y value, you're plugging those critical numbers back into the original problem to find out where the point exists. Oh, no worries. You're fine. So what'd you get for your minimum or for your maximum? Yep. Should get -12. Huh? That's you got. Okay. Yeah. Because the bottom would be -1/2, which you flip. Okay. Yeah, that is exactly what. Yeah. And the minimum value is? Huh? -4. Anybody notice an issue with this? Nothing seems wrong. Yeah. Okay. The, the minimum is higher than the maximum. They are local. But there's only two of them. So actually, if you look at this graph, that's what this graph looks like. Get rid of the red. The red's the derivative. So the minimum's actually higher than the maximum, which is odd. That's why I'm like it's one of those things like you look and go, huh? It's like and that should make you think. Like it's like that's not a normal situation that's going to happen. So like look back and see. Because sometimes you could have made a mistake. That is an extremely good possibility that when you're doing a ton of extra steps. Like that's a possibility. Now they are local, so that can't happen. It's just not a normal occurrence. This is actually what the derivative looks like. Because it goes down to -2. So down here, it's all decreasing. So that's why it's not changing on those two. All right. Yeah, find me the local minimum and maximum values for this one. So this right here is another reason why it is important to actually do the first derivative test to determine what is the minimum and what is the maximum. Because if you had skipped that step and just plugged the numbers back in, you'd have had those backwards. So by identifying that they were the min and max before you plug the numbers in, you wouldn't have made that mistake. So that's why it's important still to do that increasing and decreasing step. Yeah. 0. Oh, sorry. 1. So it'd be down here, right? Oh, you're right. I'm thinking 1. Never mind. You are correct. I was thinking, yeah, you're correct. Doesn't change my other stuff, which is good. I didn't feel like doing more complicated problems. Yeah, you're right. So 1 positive. So sine is plus or minus. Nope, that's plus. This one's minus. And yes, you can write them into Alex just like that. The sine of those two are square root of 3 over 2. This is actually what this graph looks like. So those are the two values. Now, this is one of those ones where Alex actually requires you to put in the exact value. So you can't use decimal just to get the answer. You have to plug the numbers back in and get the actual crop product. This one wasn't too difficult to do. So. Yeah, I'm gonna. Yeah. All right. So we've talked all about the first derivative. Now let's look at what the second derivative does. So the second derivative gives us what's known as concavity. So concavity it's called concave up because the graph lies above all of its tangents, and concave down because it lies below all of its tangents. The easiest way to look at this is concave up is smiling. Concave down is frowning. Okay. Right. Yeah, I think I had that first. So it is concave upward when the second derivative is positive. and it is concave downward, and the second derivative is negative. If I have a problem, I can actually have a nice graph. The points in the middles of them are known as your inflection points. So those points in between it. So those critical numbers that we're going to find again, those are going to give us our inflection points. All right, so this is just a nice little representation of what concave up and concave down looks like. So this is why I say smiling and frowning. Because you might want to go, that first section there is concave up because it's going up. You have to look at the way the curve is going. The curve is going down at that point. So from here to here, that's concave down. From here to here, that's concave down. And from here to here, that's concave down. The other 3 points, or the other 3 areas, so that is concave up, that's concave up, that's concave up. And the points in the middle, the B, the C, the D, and the P, those are our inflection points. That's where it's changing directions. Those are the values that you're going to find in the second derivative, which are the critical numbers. Those are the zeros. So when you're finding these, you're going to find those inflection points. We're not going to find the mins and maxes. We're going to find the inflection points. Now, looking at those, when it's concave down, what kind of point do we typically have in there? From what we were just looking at a minute ago, before we started looking at the concavity. Your concave downs are going to give you your local maximums. And that's going to give you your minimums. Now notice there's a couple points here and here that don't fit that criteria. And if you look, actually, let me get rid of the actual highlights. Looking at those 2 points right here and right here, is it differentiable at those points? No. They would be still maximums. Yeah. So they will still show up as those points, but they would have shown up in the other stuff when we found the first derivative and those type of things as well. So the second derivative is going to help us figure out the mins and maxes, but it doesn't guarantee that we're going to find all the mins and maxes in that direction. That's why you still have that first derivative test, which is the one we just did. Yeah. So this is the second derivative test. I'm just going to move this up. If the derivative is 0 and the second derivative is positive, then it's a local minimum. If the derivative is first derivative is 0 and the second derivative is less than 0, then it has a local maximum. I personally have not found much use for the second derivative test. First derivative test seems to work fine for this. The second derivative is really used for concavity. But you will be asked about it in one of the questions, so knowing it's kind of important. Oh, I'll let you finish writing that down. They good? All right. All right. Let's fire concavity. So for concavity, we need to find our second derivative. If it's only asking for concavity, you don't have to worry about doing the stuff for the first derivative. Now we have to do basically the same stuff for the second derivative, though. All right. Now you do the same thing we did for the first derivative. So my inflection point, or so we're concave up from negative infinity to 0, and from 3 to infinity. Or concave down from 0 to 3. If we're looking for our inflection points, this is just like you did to find the mins and maxes. We take the two critical numbers and we plug them back into the original problem. Yeah, I'm not doing that off my head. Two times 3 to the fourth. 12 times 3 is third. Plus 3 plus Huh? The inflection points are where it changes direction. They're not a min or max. So actually, I'll show you the graph.
Oh yeah.
Yeah, they're not the min and max. So, but it's okay. This is a good thing to look at the graph for. So one of the things that you should get better at. Notice how this graph kind of really dives down like that. You can change your values here. We really don't care much past -1, say 6. So we can just look at those, and it takes care of that whole big dip. So there's that. So at 0.5, it's got that change there, and the other point was at 3 and -154. So that's that point right there. So as you notice on this side over here, that's down, or that concave up. Yeah. Yeah. So that's the concave up, and then that's why it's called an inflection point. It's where that concavity starts to change. So, and if we look before it, see how this was all concave down at that point, or up at that point, down, up. All right, find me my inflection points. So this is where simplifying your problem can make your life a lot easier. So we have the three, to look at this, we have this here and it there. So we can pull it out. Oh, actually, that's not a 3. I took the 3 out. That's just x squared. So then we're left with nothing in the first one, so I have to put a 1 minus the x squared. That makes my next calculation, when I'm having to do the second derivative of this, easier to work with. Because while I still have a product, the products are nicer. Just double checking my factoring. And the other thing is, when you're simplifying it down, it's going to make life easier when you're trying to solve for 0. Find those inflection points. So now we can set that equal to 0. So we can set each piece equal to 0. Can the E part ever be 0? Yeah. So I don't even have to worry about this piece. So this one, I can pull out an x. So I have x 3 minus x squared. So I know x equals 0. And x equals plus or minus the square root of 3. Don't worry, I'm not going to make you plug it back in. And the semblance of time, because I still have a couple problems after. But you take those back in, you plug them back into the original problem here to find the inflection points. You'd plug them back into this to find where it's positive and negative. Where it's concave up and concave down. And by the way, that is an ALEKS problem. I did pull that from the ALEKS program. So. Where are you looking?
On my derivative. All right.
First derivative?
So trying to make sure I'm getting the same answer.
Okay. I think I got everything there now.
Yeah.
All right. So this question, we need to find the inflection points, and then it asks what is the how does the tangent lines actually work at those points? So actually, I'm going to pull up this top because it's easier to do when it's on ALEKS. So give me 1 second, I got to log it back in. As it kicks me out. All right. So here's the problem. So the first thing you have to do is we're going to find the first derivative and the second derivative. Exactly. So find your first derivative, find your second derivative. Oh, you're right. That solves that problem that I was just about to find out or figure out. Middle part's right. Yeah. Wait a second. That doesn't work. There we go. Thank you. That works. There we go. What happens? I'm trying to do things quickly. All right, so we got our inflection points. The two pieces of information that they need, you need to plug that back into the original problem to find the inflection point. And then you have to plug it into the derivative, first derivative, to find what the tangent lines are doing. So if I plug in the first one, that's just going to be 0, 0. Yes.
Does the domain rule still apply? Is like ever.
Yes. Yeah. So if the thing is not in the original domain of the original function, it still does not exist. Because remember, everything we're looking for, the inflection points, the mins and maxes, the concavity, all that stuff relating back to the original function. So if it doesn't exist in the original function, it can't exist, period. So yes, those domain rules still apply. Now, if we plug these back into the first derivative, if you notice on this one, all we actually care about, you don't actually need the values. You need to know if it's doesn't exist, 0, positive or negative. So you don't need to know what the exact slope is. All we need to know is basically if it's 0, negative infinity, or positive, or negative or positive. So if we plug 0 back into the first one, that's going to give me 0. So I know that's horizontal. If I plug 3 into this, that's going to be negative. That's positive. That's positive. I'm going to go with this as positive. And we plug in -2, we get negative. Oh, shoot, I forgot to switch back. The answers are the same no matter what. So actually, that's positive. So that would be. Oh, because that one's positive. Yeah. Because you get negative, positive, positive, or yeah, positive, negative. Yeah. The 15x squared rule for rules. Because you get 60 on the end one. All right, one more problem. You got it? Or did I totally screw something up? Which is totally possible. Okay. All right. This problem's actually kind of nice because they give you the first and second derivatives. So they'll make you find them, which is kind of nice. And you're going to use this basically to answer a few questions. So they're looking at the critical number of 7. Okay. So the first question asks, why is 7 a critical number of the function? So your critical numbers can be one of two places. It could be a critical number for the first derivative or the second derivative. So when you're looking at it, f of 7 equals 0. Well, no, because that's the first that's the original function. So I know that's not going to be it. That's not a critical number. So it's really going to be between those two. Does the 7 exist or not?
Or not.
The second derivative?
Yes.
I guess it could be. Let's see. Well, it exists because there's nothing in here that doesn't exist. So if we plug in 7, it does exist. Yeah. So 2, actually, I'm going to use this one. Maybe this one's actually easier. One to any power is 1. So that's 2 minus 2, which is 0. Negative 4/3 times 1 minus 2. That does not equal 0. So we knew that that wasn't it because I probably should use that. So it ends up being that one. What do we know about the tangent line at 7? Which derivative gives me that? First derivative gives me the tangent. So what's the slope at 7? 0. So that means horizontal. So this is looking at the first derivative. Find the second derivative of 7. We kind of did up here. So we get negative 4/3 minus 2. So negative 6/3, so negative 10/3. It wants the exact value. I will tell you the entire reason they're asking for the exact value is so you can't just plug it into a calculator or a graph and get the answer. That's the entire reason they're asking for exact answers. All right, using your previous answers, can you apply the second derivative test for f at x equals 7?
Yes.
So you can't plug it in. If you plug it into the graphing calculator, it's going to give it to you as a decimal. If you plug it into the scientific calculator, you can get it as a fraction if it's a simple fraction. So like the one where we had something with pi plus the square root of 3, you would not have gotten that answer out of Desmos no matter what it did. It would have left it as a fraction because it was an irrational number. So as long as it's a rational number, yes, Desmos, the scientific calculator, will give it to you as a fraction. The graphing calculator doesn't, no matter what. It's weird. Like, I don't know why they didn't put that functionality into the graphing calculator. All right. So this is the only question in ALEKS and on the homework that's asking you to apply the second derivative test. What are the two criteria for the second derivative test? The first derivative has to be 0, and then if it's greater than or equal to, right? So if it's greater than, it's a minimum. If it's positive, it's going to be a minimum. If it's negative, it's going to be a maximum. But the first derivative has to be 0 for that to work. So the first derivative is 0, and the second derivative is negative. So does it have a minimum or a maximum? First derivative 0, negative, so it's a maximum. That's the question on the second derivative. All right, any other questions? Okay, if you didn't get your test, come see me. I have your tests. All the grades have been updated in Blackboard. And for the most of you guys, it's doing pretty good. And in all honesty, the only ones that aren't doing great, it's because you haven't done the stuff in ALEKS. That's the only thing that's killing most of your grades. Your test grades have actually been pretty decent. So get to work on ALEKS, get that stuff done. If you're behind, finish up chapter 4 so you can get caught up. Did I hand it to you yet?
I think so.
Then I would go with no. Hold on one second. Let me just stop the recording.